Sure. The recording has started. Okay.
Okay. So thanks everyone for being here. Today I will tell you about normal densities in cool quantum critical superfluids. And let me start with the usual references and acknowledgements. The first acknowledgement should go to Eric Mefford, who is a postdoc with me in École Polytechnique and used to be a grad student in Santa Barbara with Gary Horowitz. And as you can expect, he's been a major contributor to this work. And in particular, he handled all of the numerics and helped quite a lot with all of the other calculations that we did. There's also some ongoing work that we're doing right now, but which isn't quite finished yet. I also wanted to thank Thomas Andrade and Richard Davison because this project came out of stuff that we started discussing 3-4 years ago. And then we all sort of went our separate ways, thinking about different things. And but well, then Eric and I took it up again and made it into what I will be telling you today. Okay, so here is the plan of the talk. I will start by giving you a brief review of superfluid effective theories, mostly superfluid hydrodynamics, just to set the stage a little bit, tell you what are the expectations that you should have, what do we know. Then I'll go through a brief review of holographic superfluids. I'll tell you how we computed these normal densities, so this will become clear what I mean by that once I've gone through the introduction and our main results. And then I'll come back and link all of this to experiments on high Tc superconductors. At any point, feel free to stop me with questions. This is sort of, I can go faster or slower on certain parts, or maybe even skip a couple of slides if we run out of time. So please just don't hesitate. I'm also kind of assuming basic knowledge of ADS-CFT, but I'm not too much entering into any details. If you want more details, you could ask, but if you feel like I'm skipping over parts a little bit too quickly, then also feel free to let me know. All right, so let's start with the basics. What is superfluidity? So superfluidity arises when we spontaneously break a U1 symmetry. And it takes its name because then the system, there's a condensate that forms, and this condensate can transport mass and charge without friction, so without any dissipation, hence the name superfluidity. Now, the usually 101 way to model superfluidity is to consider a quantum field theory where you have a complex scalar field with some Mexican hat potential, so an m squared and lambda term. Importantly, lambda needs to be positive so that it takes this kind of Mexican hat type form. And then what will happen is that you can consider a state where the modulus of this complex scalar takes a wave here at the bottom of the potential. And then you can look at fluctuations around this point. And from this drawing, it's pretty clear that you can go around, you see, around the bottom of the potential without any cost. And this is precisely what corresponds to the Goulson mode of the system. There's a gapless mode in the system, which is this mode that goes around the valley. And when you pick a value of the phase, then this is when you spontaneously break this U1 symmetry, the fact that you can go around. Now, I won't talk to you about quantum field theory, although all the calculations that I'll describe, you can do them in this particular theory here. What I want to switch to is the long wavelength, low energy way of describing the dynamics of such systems. This is also very well known, and this is due to some work by Landau and Tiza in the 60s, which generalized the equations of fluid hydrodynamics in order to take into account the presence of the condensate. So hydrodynamics is a theory of conserved quantities of gapless modes that tell you how these conserved modes relax on long wavelengths and late times. So since here we have a new gapless mode, which is a Goulson mode, the superfluid phase, then we should couple that to the conserved densities of the system, and we should give it some equation that governs its evolution. So then the equations of ordinary fluid hydrodynamics, which would just be the conservation of the stress energy tensor, and the conservation of the U1 current. So we still keep these, but now we add one more, which is this equation. So let me unpack it a little bit here. So this curly phi is the superfluid phase. So you see that it enters the equation through its gradient. Then you contract it with the fluid velocity. So for an equilibrium state where there's no background superfluid velocities, this u would just be u mu. So this would be 1, 0, 0 for 2 spatial dimensions. So you can see that when you contract it with the mu phi, this simply gives you a time derivative. It tells you that the time derivative of phi is related to the chemical potential. The underlying reason for this is simply the fact that we're spontaneously breaking a U1. So the same U1 that rotates the complex scalar field actually sources the gauge field. So this is why you have this relation between these two quantities, between phi, the superfluid phase, and the chemical potential. Now, as you may be familiar with, these equations, they're not enough to actually solve the system because we don't know what T mu nu and J nu are. So we need to give these conserved currents, the stress energy tensor and the U1 current, we need to give them so-called constitutive relations. Basically, we need to write down what they are in terms of the known quantities of the system. So these known quantities of the system, well, they're what you might expect them to be. They're thermodynamic variables, which you then let fluctuate. So the goal is to write these objects, T mu nu and J nu, in terms of energy, charge densities, etc., and their fluctuations in a way which is consistent with thermodynamics. And then you let these fluctuate and you expand them order by order in gradients of time and space. And one of the basic assumptions of hydrodynamics is that these gradients are small so that this expansion in gradient is meaningful. So here, throughout this talk, I won't really use anything that has to do with the gradient expansion because I don't need it in order to tell you what I want to tell you on the normal and superfluid densities. So actually the constitutive relations that I wrote here, they're just ordinary, they're just ideal hydrodynamics. This is just thermodynamics, if you like.
Blaise, can I ask something?
Yeah, sure.
So this third equation, u dot del phi is mu, is it well defined when if you put in dissipative terms in T mu nu and J mu? Because
no, exactly. So this would only be exactly. So this somehow is not quite on the same footing as these two equations. Sorry, let me erase some of the clutter. Yeah. So these, they really follow from the conservation of a charge. So these are word identities, if you like. So what changes when you go through the gradient expansion is the expression for T mu nu and J nu that you plug in these equations, but these equations themselves, they're protected by symmetries. However, this is not an equation which is protected by symmetry. It's not on the same footing as the previous two, because the Gaussian mode is not a conserved quantity. So in particular, when you start expanding this in gradients, so I'm getting a little bit ahead of myself, but here you would write plus all the gradient terms, and here the same, plus all the gradient terms. But then you would also write here plus all the gradient terms. So at this point, this equation is purely non-dissipative. There's no dissipation here. And the dissipation would come in through these extra gradient terms that you normally should write if you want to include dissipation in the system.
Yes. So what I wanted to also ask is this U, whether it should be thought of here as the energy current velocity or the charge velocity, because
So okay, let me go through this now. Okay, let me describe the constitutive relations. So let's see. For a system at rest, then thermodynamics would be characterized by the first law. So let's set aside the superfluid for now. And the first law you can write like this. So right, it tells you that the variation of the pressure is given by the entropy times the variation of temperature plus the charge density times the variation of chemical potential. And then you have another relation, which is the SMAR relation that tells you that E plus P is Ts plus mu rho. And essentially this relation arises from requesting that these equations are compatible with the first law. And now you can show that you should write the ideal constitutive relation for the stress energy tensor for the current as E plus P times u mu u nu plus P A times u nu, where A times u nu is just a Minkowski metric. I'm considering a flat background here. And u mu for now, for a fluid at rest, would be just what I wrote before, 1, 0, 0. So in this case, this would simply ensure that T0, 0 is, sorry, I'm writing very badly, is epsilon, and Tii is P. Now, because I'm assuming relativistic symmetry, I'm free to boost the system and to let u mu be non-trivial. So now u mu doesn't need to be just 1, 0, 0. I can boost it. And in the same fashion, the current you show is equal to the charge density times the velocity u mu. So I think to answer your question, u mu would transport both charge and heat in this case.
Yeah, but I was talking, if you include dissipation, then it's important to understand whether u is actually the charge transport velocity or the energy transport velocity. So in this case, what's the right way to think about this equation that you wrote down, u dot del is mu, when you include dissipation?
So when I include dissipation, I wouldn't be changing the left-hand side. I would just be changing the right-hand side.
Yeah, but
I would say that U transports both charge and heat, because in this system I could write the entropy current, Js mu, and this would be Su mu.
Yeah, that of course is the leading order term. That has to be the case.
Yeah, plus dot dot dots. But then, so then when u mu flows, it transports both charge and heat.
Right.
It doesn't just transport one or the other. At least not in this frame.
Yeah. At the leading order, you can only have one u because everything is in equilibrium. There is only one velocity or one frame, right, for the full system. But when you include dissipation, then of course there are different frames, like the Eckert frame or Landau frame, right? That uses different definitions of u mu, and then the constitutive relation changes accordingly. Because
yes, that's right.
So in that case, the question is, how should I think about this equation, u dot del phi is equal to mu, whether it is defined with a particular frame in mind when you include dissipation? This
equation is an equation that only knows about thermodynamics.
Okay, so this is, okay, I see. So this doesn't, okay, I see. So this.
So whatever definition you pick for u mu when you start including dissipation would only change subleading terms and gradients that appear here at subleading order.
I see. Thanks.
Yeah. So I agree that changing your definition of u mu will change the constitutive relation and will change this equation will look different, but it will look different in the sense that the terms that you need to add will look different depending on your choice of frame. Okay, but this ideal part, the ideal part is not going to change exactly in the same way that the ideal parts here do not change.
Yeah, sure, of course, yeah.
Okay, so this is why I'm not gonna, I'm not gonna worry about any of these issues here, because the objects I'm interested in, which are the charge densities, it's enough to know about thermodynamics. In order to discuss them, I don't need to include dissipation, which is a nice simplification.
Can I ask a question?
Yes, please.
So in the expression for the conserved current, J mu is equal to rho n,
Yes.
So the first part tells us that the normal component of the superfluid is being transported with this u velocity vector, right?
Yeah, so sorry, I didn't get to this yet, but yes.
Oh, sorry,
yes.
okay.
Yeah, this. I sort of got derailed in the way that I wanted to present things, but yes, let me now go through this. So right now, everything I was saying mostly applied to fluid hydro, with the exception of the discussion we just had on this Josephson relation. But now let's see what happens when we do include the coupling to the Goulston mode. Coupling the Goulston mode doesn't simply add one more equation. It also adds new terms in the constitutive relations. And the guiding principle is that you should add terms that are allowed. But then since we're still only talking about thermodynamics, we want to add these terms in a way which is consistent with thermodynamics. So this uniquely fixes all of these terms. And in particular, we see that there's an extra contribution to the first law, which is this one right here. So it tells us that now the pressure, another way of saying this is that the pressure is now a function of, say, temperature, chemical potential, and this quantity right here. So maybe, let me call this maybe psi squared. So there we go, psi squared. So there's now a new thermodynamic quantity that characterizes the system, which we can think of by virtue of this equation. This now is a purely spatial term. Basically, this combination here subtracts off the time component of the vector because of this equation. So this tells you that there's some d mu phi. At equilibrium, this will be mu, and then there will be some spatial gradient. And it's telling us that the pressure and all other thermodynamic quantities depend on this spatial gradient squared, which people usually refer to as the superfluid velocity. So there's a new quantity, there's a new source in your background that you should take into account whenever you think about thermodynamics. Now we come to these extra terms in the constitutive relations. So as you were mentioning, there's now a new term in the current. The current is made up of two terms at ideal order. One is the usual term, the normal charge times u mu, which tells us that some of the charge in the system is being transported by the usual fluid velocity. And actually, this is the part of the system that when you include dissipation is producing dissipation. But now there's also a new piece, which is proportional to the superfluid velocity, d mu phi. And that has a coefficient rho s, which people usually call the superfluid density. And that's the part that doesn't produce any dissipation. So this is why sometimes people refer to superfluid hydrodynamics as the two-fluid model, because they want to think of it as some normal fluid intertwined with the superfluid. So a normal dissipative fluid and a superfluid, which is dissipationless. This is a little misleading because it's not like you have two conserved charges that are, making up your system. You still only have one charge, which is this rho, and which is governed by one conservation equation, which is the usual d mu j mu equals 0 conservation equation. It's just that now we can split the current into these two pieces and give them, give their coefficients these different names, the normal charge and the superfluid charge. All right. So our main objective in this talk will be the study of what rho n and rho s are at 0 temperature. We want to know how the superfluid part and the normal part of these systems behave as we go to 0 temperature. Any other questions on this before I move on? Okay, good. So this coupling of the Goldstone mode has important consequences.
Sorry, can I ask you a very quick question?
Yes, please.
Yeah. So, you know, when you say that you are going to take the zero temperature limit, I presume that your you know, what is your fluctuation length scale? So, are you going to still presume that your fluctuation length scales are bigger than the as you approach the zero temperature?
I will very carefully never work at exactly zero temperature.
All right. All right.
Yeah. Yeah. I understand why you're asking this, and yeah, I won't be at exactly zero temperature. I mean, well, when I'll be at zero temperature, you'll see what I mean. When I'll do hydrodynamics, I will be at small finite temperature. I'll be at small temperature compared to the chemical potential, let's say.
Your temperature is smaller than your chemical potential, and your fluctuation length scales are bigger than both the length scales. Is that right?
That's right. Yes.
So 1 over temperature is the temperature length scale.
There we go. So wait. So in the I'm getting ahead of myself a little bit.
Sorry.
I want to
continue. Yeah.
To consider a regime where the temperature is much less than the chemical potential, but then I want omega and k, so the frequency and the wave vector, to be much smaller than t. All right.
All right.
So I can still do hydrodynamics in this sense.
So it's not strictly zero temperature, right?
No, I want okay. Maybe let's rediscuss this at the end of the talk. I think it's a very interesting question, but it might be clearer so that I don't get too much ahead of myself. Then you'll see what I'm doing. Okay, but I won't be at exactly zero temperature, although some of the review material I'm going to give you now is at zero temperature. It starts from I'll go from high temperatures to low temperatures. But when people do, let's say, superfluidity in quantum field theory, you start from zero temperature and you heat it up a bit.
Yeah, okay.
Thanks. Okay, so the coupling to the Goldstone mode has important consequences on the spectrum of hydro modes. Just for reference, I've put here what we have for an ordinary fluid. In an ordinary fluid, we would have two sun modes that describe fluctuations of energy and longitudinal momentum. And well, these are the, these would be the modes that have, superfluid. Okay, yes, a sun mode, there shouldn't be a squared here, obviously. Okay, a sun mode is a mode which is linearly dispersing. So its dispersion relation omega in terms of the wave vector q is linear. The first term is linear, and then there may be higher order corrections. And for this ordinary sun mode, then the sound velocity squared would just be dp over dE with constant entropy. So these are the modes for an ordinary fluid. And then we would have two diffusion modes. So these two would have omega is minus ID q squared plus higher order terms. And they would describe fluctuations of transverse momentum. So this would be the guy that is set by the shear viscosity of the system, for those of you who know about this. And the other one, which is in the longitudinal sector, would describe fluctuations of the ratio of charge over entropy. So this is the spectrum of gapless hydro modes for an ordinary fluid. Now for a superfluid, what happens is that intuitively you can sort of understand why this is happening. The condensate, the phase of the condensate, it is intimately related to charge. You can see this from this Josephson equation. So you can expect that it will couple strongly to this charge diffusion mode. And indeed, what it does is that it turns it into a sound mode, which people usually call superfluid second sound mode. So now in the system, we have two types of sound modes. We'll have a sound mode that describes propagation of energy and longitudinal momentum. And then we'll have a different sound mode with a different velocity that describes the propagation of the Goldstone and of charge and heat. And the velocity for the second sound mode takes this expression in relativistic hydrodynamics. Yeah, so that's the main point. Once you turn on a superfluid, then sure, the other expressions might change a little bit, but the most important consequence, at least from my perspective, is that a new sound mode appears, which is made up of the original charge diffusion mode and coupling to the Goldson mode. And it has this velocity. Now, as I said, in this talk, I'm mostly interested in the normal and superfluid densities, which are, in fact, infrared parameters. By this, I mean that they're parameters that appear in the effective theory that describes the system at long wavelengths. They're not UV parameters in the sense that if you give me a microscopic theory where you know that that some order parameter condenses by spontaneously breaking a U1 symmetry, then this Hamiltonian, let's say, is not originally written in terms of the normal and superfluid densities. It's written in terms of microscopic parameters. And then if you're powerful enough, you can take a continuum and a long wavelength late time limit where you will see that all the dynamics is contained in the evolution equations of the current and the stress energy tensor. And then you will be able to compute the normal and superfluid densities. So the main reason why I'm saying this is that these two quantities, they're not related in a simple way to the charge residing in the condensate, which is a UV parameter. You know, you might simply ask, if I have superfluid helium, helium-4, then how many atoms are actually condensing at 0 temperature and how many atoms are not condensing at 0 temperature? Well, in superfluid helium, people have measured that the condensate at 0 temperature contains less than 10% of the total number of atoms. Yet, another well-known result is that in helium-4, the superfluid density at 0 temperature is equal to the total charge density, to the total density, not charge, sorry, to the total density. So even though not all the system has condensed, not all of the atoms are sitting in the condensate, the total density, all the atoms behave as a superfluid. There's no normal component left at exactly 0 temperature. Do you see what I'm trying to, this is an important point.
So I have a question.
Yes, please.
So, I mean, if you cannot distinguish the superfluid component from the normal component, then how does one measure and find out this fact that only 10% of the...
You do distinguish them.
No, I'm saying at 0 temperature in superfluid helium, you're saying that the superfluid...
I'm saying that at 0 temperature in superfluid helium, there's no normal charge left.
Right.
There's no normal component. It's not that you cannot distinguish it. It's just that it's vanished with 0 temperature at exactly 0 temperature.
Right. So then my question is like, how does one determine that how many percentage of the atoms are participating in the condensation? That's what I'm asking.
You mean experimentally?
Yeah, I mean, like
a question that I don't know the answer to.
Okay.
Though I think you can probably just also calculate it. Okay, okay, I know I don't want to say anything wrong. It's a good question that I should look up for future talks.
May I just make a comment on that?
Yes, please.
Shiva. In an experiment, it has been shown even microscopically in the spirit of this very classic Andronic-Castelli experiment where there's a paddle wheel or it's a torsional pendulum inside the liquid. Bulk liquid superfluid helium, people have also used molecules and the rotations of molecules to essentially do microwave spectroscopy and found that, I mean, the typical molecule used in this is OCS because its rotational spectrum is very well known. And it's a very famous science paper. The OCS molecule rotates freely, but with a shell of solvation shell of helium adhered to it, and the rest of it rotates rather freely, and one can recover very clearly the the rotational modes of this slightly composite system. And that was done with helium-4, and then people sunk in a little bit of helium-3 in it, so that the solvation shell has some helium-3, and then compared the two results. Because helium-3 is not superfluid at at temperatures like 0.5 millikelvin or so, and the rotational spectra were different. This gave a very good idea of how, on an atomic scale, one could measure through measurements in a superfluid.
Mm-hmm. Yeah. Okay. Well, I'd be interested in the reference if you have it on the hand.
Sure.
Me too. Me too. Thank you so much for that.
So one important point also is that here, what I'm quoting, this result I'm quoting here, applies for systems with only helium-4. It's also well known that if you make a mixture of helium-4 and helium-3, then this will typically be non-zero at 0 temperature. But for a system with a single species of atoms, then this result is true. So this is something you can compute, and the way that it's computed in conventional and in textbooks is that you assume that at 0 temperature, the system consists only of a gas of 3 phonons. This is how the superfluid phase, the Goldson mode, is called. And then you just impose Galilean Lorentz boosts and assume both statistics because you're interested in helium-4. Then from there, you can determine the pressure, the entropy due to these superfluid phonons. And after boosting, using your Galilean boosts, you can use the constitutive relations. So these equations, suitably truncated for the Galilean case, and determine what rho n is. And you find this result. You find that at small temperatures, rho n is given by some prefactor times t to the 4, which is actually exactly equal to the entropy of the phonons times temperature divided by c squared, where c is the how do you say this? C is the velocity. Your starting point is that you assume that in your system you have a linearly dispersing mode with some velocity c, which is your Goldson mode. So this is a very nice result, and the reason why I'm quoting it is that I will be coming back to this result and show how what we obtained relates to this. And this is obtained in a limit where c is much less than 1 in natural units, so much less than the speed of light. So now you can plug these results in the expressions for the sound modes in Galilean invariant superfluid hydrodynamics. For normal first sound, this is what you would get. You get that the first sound mode goes like c squared. And the superfluid second sound mode, c2 squared, which has this expression for Galilean invariant hydrodynamics, goes like c squared over 3 in g equals 3, because this is for helium. But if you do this in arbitrary number of spatial dimensions, you would find c squared over d. And this last result is well known. This is a prediction that Landau made for the low temperature behavior of second sound in these spatial dimensions. So again, here I'm trying to give you some reference points of what you would typically read in a textbook on superfluidity. Now, you can recover these results a bit more rigorously in the relativistic case using a framework which was devised by Damson in 2002, which he called a quantum effective action for relativistic superfluids. And the starting point is based on symmetries. It assumes that the system only depends on a fundamental variable, which is d mu phi squared. And this is consistent with how the superfluid phase transforms. So it's a good starting point. And then you pick Lagrangian to be some arbitrary function of x. When you go through the calculations, P turns out to be the thermodynamic pressure, so that's why people call it P. And then from there, once you solve the system around its saddle point, you can recover all of the superfluid thermodynamics, etc. Now you can generalize this to a small non-zero temperature, and And there you would also have a normal fluid component and a normal density, the rho n. This was done by Nicolis in 2011. And then you can go one step further. You can also determine what is the low temperature dependence of the normal density. So this is true at low temperatures, T much less than mu. And you would find St over mu CIR squared 1 minus CIR squared, where CIR is the effective light velocity in the IR. So here, what I mean by this is that this is an IR theory. And you're assuming that it's relativistic, so this has some speed of light, but this is not, the speed of light need not be the same as the UV speed of light if your system flows between two relativistic fixed points. It could be some different, it could be renormalized. That's why I'm calling it CIR. Actually, we'll see this very explicitly when I turn to holography. So this is compatible with the previous expression that I was showing you here. So this expression, if you take the non-relativistic limit, then CIR is very small. You're only left with this factor. Then you arrange the factors of mu, etc., in the right way, and you recover the same thing. So it's a very nice cross-check of this earlier literature. So what this teaches us is that the normal density in superfluids that are described by some IR fixed point, which is just a free gas of phonons, of superfluid phonons, the superfluid density in these systems vanishes like the entropy times temperature in a very specific way. Now we could ask, do all superfluids necessarily fall into this universality class, so the almost free gas of phonons? Well, one other check that you can do is you can look at BCS superconductors. You can compute there what is the normal density and the superfluid density. And in the systems, you find that it's exponentially suppressed at low temperatures. You might want to go beyond BCS superconductors and see what happens in strongly coupled superconductors, such as high Tc or holographic superfluids. The reason I'm mentioning high Tc superconductors is that people know that these are not just conventional BCS superconductors. And in fact, there's evidence that the picture we just described is not always correct, both from high Tc superconductors and holographic superfluids. So let me describe these two things in turn. Are there any questions at this point before I move on?
Yeah, I would like to ask something here. So
yes, please.
The description of SON is exactly at the critical point because the goldstone is massless. Could you also go a little bit around the critical point and give a similar description here?
Critical point. I'm not sure. He doesn't. You mean fixed point?
Yeah, fixed point because
I'm not sure
I have no mass here, right? Because you're.
Yes. But then you see, the fact that phi is massless, this is a consequence of symmetry. So if you want to make it massive, then you have to break the symmetry explicitly.
Yeah, so the scenario I have in mind is that the mass is scaling with the as you approach the critical temperature as some exponent of T minus Tc, and whether you could also incorporate that kind of some kind of exponents like that in this description, where
but you see, this is a zero temperature description. And we know that typically the system condenses not at T equals 0, but at Tc, which is non-zero. And close to Tc, there's another effective description, which is the Landau-Ginzburg free energy, which is valid for temperatures close to Tc. So you can think of these two descriptions as describing two different regimes.
Right, but you can also have quantum criticality, right? You can also have quantum criticality where you can...
Yeah, so I understand. You want to move in a different direction in the phase diagram, okay, I'm not sure. I don't know. I don't know the answer to your question. I think it's an interesting question, but I don't know if people have tried doing it.
Thank you.
yeah, you could certainly imagine including, say, a magnetic field or disorder or something like that. And that would typically suppress superconductivity at some point for high enough field or high enough amount of disorder.
May I just make a comment?
Yes, please.
In experiments on helium-4, actually, even having an impurity doesn't seem to suppress the superfluidity. Not until some limit, I would say. I don't know what that is, but it would literally sink molecules inside that, or some of them are even held on the surface. But then experiments, as far as I know, show that you still have superfluid behavior in helium, or even like people try to inject electrons inside inside the superfluid, and still the sort of behavior persists.
Mm-hmm. Yeah. Yeah, it's probably a bit easier to suppress superfluidity with an actual superconductor, because then you can use a magnetic field. Okay. Ian, can you tell me how am I doing with time? Because I don't have a clock right here. And
you have half an hour more?
Half an hour more. Okay, good. Okay, so let me tell you why I think this picture that I've just described you is not always accurate for just any superfluid system. So high Tc superconductors are well known. They're a well-known mystery in condensed matter because they become superconducting at a very high critical temperature, which is not that you cannot capture it using BCS theory as you would normally do for a conventional superconductor. Moreover, there's this very strange phase diagram right here in terms of temperature and something called doping. Doping tells you about some chemical substitution of elements. And what people show is that at very low dopings, these systems are a Mott insulator. Then as you increase the doping, you increase the number of charge carriers, the system becomes superconductor. But this superconducting region somehow seems to arise from a strange metallic region. It's strange because it has laws that are at odds with conventional Fermi-liquid theory. And then at high doping, people think that you recover conventional Fermi-liquid type metal. So the law is usually that at least this side of the phase diagram is well understood for overdoped cuprates, for overdoped high Tc superconductors. Yet in 2016, there was a study by Blaise et al. Where they measured the superfluid density in this region of the phase diagram. So for very overdoped lanthanum, strontium, copper oxide films. And they found surprising features. First, they found a superfluid density which is anomalously low, which you cannot really see on these plots that I'm showing you, but in terms of numbers, they're much lower than you might expect compared to the total density of atoms, total density of charge carriers. And moreover, as you can better see here, it has this linear behavior with temperature as you go to low temperatures, while standard BCS theory in the presence of disorder would predict the T-squared behavior. And there's a whole discussion on why they don't think that dirty BCS can account for this, etc., etc. I don't really want to get into the details of all of this. But so these are two surprising features that don't quite match what you would expect from weakly coupled BCS theory. Then there was another set of measurements by Mahmoud et al., with Bozovic also being a co-author, where they measured the AC conductivity of these superconducting films. And what they show is that there's a very modest loss of spectral weight below Tc. So in a conventional superconductor, you know that there's this exponential gap. So as soon as as you cross Tc, as you go below Tc, you expect that the normal density, the weight of the Jude peak in your AC conductivity becomes exponentially suppressed, and everything goes into to higher frequencies. You gap this out. But here what these plots show, so they show the real part of the conductivity where you would normally see the Judah peak. So, you know, the Judah peak of an ordinary metal, this would be something like this, right? This would be real part of sigma, and this would be frequency, and you would expect the conductivity, so the complex conductivity, to go something like the Judah frequency squared, gamma minus I omega. This would be your Judah peak. And this Judah frequency squared is telling you about the spectral weight inside the peak, and is proportional to the normal density of charge carriers. So the fact that there's very little, you can see that here, as you go below Tc, this is clearly not being exponentially gapped out. You can think of the difference between these two curves as a measure of the density of carriers that go into the superfluid density versus those that stay in the normal density. So in fact, what these authors did is that they extracted these quantities and they plotted them here versus Tc, so the value of the critical temperature. And they plot several things. So they plot the number of, they plot the normal density or the normal ratio. So as you here, you can think of rho n over rho total. And as delta is the number of, is the superfluid fraction, rho s over rho total. So the yellow dots here are the sum of these two quantities, and they asymptote to 1, as you can see, where rho total is determined from the measurements in the normal state. So this is a good cross-check that, you know, they're extracting things consistently. But then what they show is that at very low temperatures, so this is T equals 1.6 kelvins, which for all intents and purposes experimentally is almost 0 temperature. Then you see that, for instance, here, there's most of the system is normal, and actually a very small fraction of the system is superfluid. And that's, like I was saying, completely at odds with BCS, because BCS would tell you that the normal density is supposed to be exponentially suppressed. So you would normally expect these two curves to be reversed. A very small normal fraction and a very high superfluid fraction, very close to unity. So from this, they concluded that there's something wrong with the BCS picture. Okay, so this is some motivation on the experimental CONMAT side that I'll come back to towards the end of the talk.
Question?
Yes, please.
So just to be clear, what this graph is showing is that as the critical temperature drops, SU, so SU is the normal density.
Yes.
That is increasing, and the superfluid fraction is decreasing.
Right, but not just that. It is, let's say that you would expect the hierarchy between these two quantities to be reversed in a conventional BCS superconductor.
Right. Okay. So yeah.
Of course, you might expect that something weird happens when Tc becomes really, really small, because then, you know, the system almost doesn't want to be superconducting anymore. But when you're here, Tc is still is quite sizable, so you don't.
Exactly. Right. It's weird. Yes. Thanks.
Yeah. Good. So let's now turn to another class of strongly coupled superfluids that we can describe using gauge gravity duality. This is my very sketchy introductory slide on ADS-CFT, just in case. Well, for those people that are familiar with this, this is clearly not enough. For people that are not familiar, this is also not enough, but might give you a little enough of a hint of what I'm discussing so that you can connect the dots. So what we now understand, since this paper by Malasena in '97, is that gravity in so-called Untitled spacetimes, which are solutions to Einstein's gravity with a negative cosmological constant, that these theories of gravity are dual to certain strongly coupled quantum field theories, which you can think of as matrix theories in the large n limit, where n is the n of SUN, the gauge group of the matrix theory. And importantly, there's one less space, you lose one spatial dimension in the process. So you have gravity here in d+1 dimensions and quantum field theory in d dimensions. I won't go through the evidence for this or even the details, but the main point to take away is that you map the complicated dynamics of these strongly coupled quantum matter, so n equals 4 super Young-Mills, etc. You map these to solving Einstein's equations in a certain type of spacetimes. And this is conceptually much simpler because if you have a strongly coupled quantum field theory, you don't necessarily know what to do, since you cannot do perturbative expansions, but you can do that when you have Einstein's equations because these are weak field gravity equations. Now there's a holographic dictionary between these two descriptions that tell you, if you compute an object on the gravity side, how do you relate it to one of the observables you might be interested in on the quantum field theory side? And this is well established. And in particular, if you want to describe the thermal non-zero density state in the quantum field theory, you want to consider a charged black hole in Untitled Chapter. Now, in order to continue with the talk, what we care about are systems that exhibit superfluidity, so spontaneous breaking of a U1 symmetry. So this is what we want to realize in our gravity system. And this was originally done in these papers by this gentleman over 10 years ago. And what they were doing is they were coupling a charged complex scalar to gravity. So they were looking at this type of action. So here, notice my conventions. I have an action in d+2 dimensions. So d is the number of spatial dimensions in the boundary. And there's one more dimension for time. And then there's one more dimension that describes this radial coordinate, which spans the space-time from the boundary, where I define the quantum field theory all the way to the black hole horizon at the other end of space-time, roughly speaking. So this gravity action has the usual ingredients that you would expect in applied holography. It has Einstein gravity under the form of the Ricci scalar. Then it has a U1 gauge field with just a Maxwell field strength term. And then it has a charged complex scalar with some potential. Now, what these people found is that if you take the system to low enough temperature, then this scalar field eta wants to condense close to the horizon. So it forms this condensate, this charged condensate in the middle of the space-time. And now you have a qualitatively new solution, a new black hole solution that has a lump of charged scalar fields sitting outside the horizon, which is here. And here you have your condensate. And that system spontaneously breaks the U1 for pretty much the same reason that the quantum field theory of a complex scalar with a Mexican hat potential breaks the U1. This thing picks up a VEV, and that breaks the U1. So the original solutions that were constructed back then were very quickly shown to obey the Landau-Tisa model of superfluid hydrodynamics that I was telling you about in the introduction. So that put this correspondence on firmer footing. The fact that if you consider this type of action, you spontaneously break a U1, and then you recover exactly the field theory expectations that you should have when a U1 is spontaneously broken. So this was a nice cross-check that these gravity solutions were doing what people wanted them to do. Now, what we wish to do is to compute the normal and superfluid densities in these holographic superfluids. For this, if you remember what I was showing you at the beginning of the talk from superfluid hydrodynamics, what we need to do is to extract the one-point function. In particular, we will be interested in the Tx component of the stress energy tensor and the X component of the current, which I wrote here, just to remind you what they are. And so from the knowledge of these one-point functions, we'll be able to extract rho and rho s, which is what we're interested in. Now, the way we do this holographically is that we consider perturbations of the bulk fields. So perturbations of the metric along the Tx component and perturbation of the gauge field along the X direction. And the nice thing is that, as I was stressing at the beginning of the talk, these are quantities that you can access just using thermodynamics. So you can work at zero frequency and zero wave vector, and that gives access to all the required information, as well as the superfluid velocity after a gauge transformation. And this is something that Herzog and Yarom did very quickly after the original solutions were constructed. So here I'm just going to revisit some of this earlier literature and try to explain some aspects of it or check how some of it is consistent with what I was telling you at the beginning of the talk. So let's see what these people found. In 3 spatial dimensions, so for 5-dimensional gravity solutions, they computed, so here, I don't know if you can see very well, but this is rho s over rho in the vertical axis versus T over Tc. And there are varying parameters of the model, which are these U and Q. It doesn't matter what they are. And what they find is that, you know, there are some values of the parameters, so these two, where the superfluid fraction, rho s over rho, nicely goes to unity as T goes to 0. So as we would expect, using this effective description of the system at 0 temperature as a free gas of phonons. And the same here. You see that for all of these values, everything goes smoothly to unity at 0 temperature. But then there are other values of the parameters where something weird appears to happen, where this superfluid fraction does not appear to want to go to unity at 0 temperature. So in particular, we've revisited, so these, you can see that these solutions don't go to very low temperatures. T is not that much less than Tc, but we've gone to much lower temperatures and confirmed that these things don't go to unity at all. So you might ask, why? This seems to be completely at odds with everything I've been telling you before in the introduction.
Blaise, what is this parameter U?
So U is, I think, the quartic coupling in the potential. The Sumo Mexican had potential for the, so I think this parameter, so V of eta, this is going to be some m squared, eta squared, m squared, eta squared minus plus U eta 4, I think.
Yeah, thank you.
It's the quartic coupling with the right sign that I think is this one, but off the top of my head, I might be getting wrong. Good, so our strategy is to try to explain these results and understand why the superfluid fraction should not be unity at 0 temperature in these systems. So at low frequencies, we can compute the hydrodynamic prediction for the current retarded Green's function, and you find this. So you find, this is very well known, you find that there are 2 contributions. One comes from the normal part of the system, and it has to do with the fact that translations are not broken in the system. So that's why it's proportional to the normal density. It has to do with the dynamics of the normal fluid. And another one is proportional to the superfluid density. And this is the well-known source for the superfluid delta function. Holographically, the way that we compute this is that we look at the perturbation of the gauge field along the X direction, solve for it using Einstein's equations, the coupled Einstein-Maxwell equations, and then we expound the solution that we get close to the boundary of ADS, which in these coordinates is U going to 0, which is a different U from the previous slide. This is the radial coordinate. And we look at the first coefficient and the coefficient which is linear in U, take the ratio of these two, and this is giving us the retarded Green's function. Now, since here we care about thermodynamics, we can actually work at omega equals 0, at 0 frequency. And so for people that know a bit more about ADS-CFT, what we compute is the solution to the omega equals 0 equation of motion for delta x, delta AX, which is regular at the event horizon. And regularity means regularity in Eddington-Finkelstein coordinates. So what we do is we compute this regular solution in a small temperature expansion, and that should give us access, it does give us access to the normal density at low temperatures. I won't go through all the details of the calculation, also because they should appear in this upcoming paper that is not yet out, but this is something we've done, and then we've also checked numerically. But in a nutshell, just to give you the main points, is the low temperature expansion that we find differs qualitatively depending on the spectrum of deformations around the ground state of the system. So by ground state of the system, I mean that the system is described in the IR by some zero temperature geometry close to the horizon. And then we look at how this extremal geometry is connected to the UV ADS. And it's connected by some set of irrelevant deformations. So modes, radial modes. And depending on how these modes interplay, then we find qualitatively different low temperatures expansions. To be a bit more precise, there are two deformations that are particularly important for our purposes, and you can see them in this equation. So this is the delta AX equation, which I've rewritten in order to show this is the spatial background metric, this is the time component of the background metric, the radial component of the background metric. Primes are derivatives with respect to the R coordinate. And so frequency we can set to 0. Then you can see that there are two mass terms. There's a mass term that comes from the fact that there's a non-trivial gauge field, background gauge field in the system. So this mass term comes from the F squared term in the gravity action. So it would be there for any non-zero density state. It has nothing to do directly with the spontaneous breaking of the U1. Then there's another term, which is this one, which comes from the covariant derivative in the action. So that term knows about the spontaneous breaking of the U1. So I can, roughly call these two deformations as the particle hole symmetry breaking deformation and the U1 symmetry breaking deformation. And what our computation shows is that the zero temperature limit of rho n is actually controlled by the competition between these two deformations at low temperatures. So we need to check which of these two deformations dominates, which one is the least irrelevant. But this will depend on the ground state of our model. And so for this, we need to understand the ground states of this holographic system. Now, these were studied also a long time ago by Gupser and Nelor, and also Horowitz and Roberts. And they found that there are two types of IR geometries. So by IR geometries, I mean the geometries that describe this end of spacetime, so the near horizon, near extremal part of spacetime. They found that you could either have another copy of ADS with a different radius, or that you could have a so-called Lifshitz geometry. So this is what a Lifshitz geometry looks like. And you can see that it takes its name Lifshitz because you can check that it's invariant under T goes to lambda Z times T, and then R goes to lambda R, and Xi goes to lambda Xi. So time and space in the field theory scale differently, anisotropically parameterized by this dynamical exponent Z. So this is why these are Lifshitz metrics. Now, whether you get the ADS2 or the Lifshitz geometry in the infrared, so whether you go to one or the other of these two types of fixed points, depends on whether the gauge field is irrelevant at zero temperature close to the horizon or not. So it depends on the dynamics of the gauge field in this region. This is what these people showed. So then when you go through the calculation and you take into account this knowledge about the two types of ground states of the system, you find that when this dynamical exponent z is between 1 and d plus 2, where d is the number of spatial dimension, then the condensate deformation dominates. So this one, this is the condensate deformation. This is the more important one. And then when you go through the calculation, you find this result holographically, which exactly matches the EFT result that we saw earlier. And in this case, it held for z equal 1. But now we find that it also holds away from z equal 1, but for values of z that are low enough. So in this case, we have our conclusion would be that the ground state of the system still looks like a gas of free superfluid phonons. So this is, if you like, a free IR fixed point. On the other hand, if z is large enough, so for spacetimes with a sufficiently large value of the Lifshitz exponent, then it's the other deformation that dominates. It's the deformation that breaks, that sources density. And then what we find is that the normal density goes to some constant. It no longer vanishes at 0 temperature. And here, just to connect back to the discussion we were having at the beginning of the talk about the fact that rho n and rho s are IR parameters and not UV parameters. In all of these ground states, all through here, the charge of the solution sits entirely at 0 temperature in this condensate. So I'm always describing geometries where at 0 temperature, all of the charge has been expelled from the horizon and everything sits in the condensate. So you might think of these as systems where all the charge carriers condense at 0 temperature. And yet, depending on the value of z, I can have a non-trivial normal charge at 0 density, although all the charge is in the condensate. So this is just to say that these quantities, they are not simply related to one another, rho n and rho in. So this is just
Can I just ask a clarification about the, so yes. What was your RH in this formula in the first equation?
Here?
The horizon radius, yeah.
So, so what do you mean what it is?
I mean,
this is the horizon radius. So here I'm always considering spacetimes that have a small temperature. So
right.
T much less than mu.
So RH is also dependent on temperature, is that right?
Yes. Yeah. So typically RH is T minus 1 over Z.
Very good. So now is it possible to somehow tune your Z so that, oh, it goes as minus, is that right?
Yeah.
I was wondering that even in the first case, you could actually make rho n finite by tuning the Z. But
no, yeah.
It's possible?
Well, so what happens here, no, actually what you see here, maybe this is worth commenting, thanks for reminding me. So if I take this formula, S goes like T to the D over Z, as you would expect in a Lifshitz-invariant phase. And then CIR squared goes like T to the 2 minus 2 over Z. So now this is saying that rho n, so this time will always go faster to 0 than 1. So at very low temperatures, I can just neglect it.
Right.
So now rho n goes like T to the 1 plus D over Z plus 2 over Z minus 2, which is rho n going like T to, sorry, let's get this right, D plus 2 minus Z over Z.
Mm-hmm.
So you can see that if Z is less than D plus 2, then rho n
Oh, I see. So it's
is 0.
you are saying that it's this fact that gives you the second formula. I see. I see. Okay.
The second, well, more precisely, it tells me that for z greater than d plus 2, then this formula must be breaking down because it doesn't make sense that rho n diverges at 0 temperature. And actually, when you do the calculation more carefully, assuming z greater than d plus 2 from the start, you would find that it doesn't diverge. It goes to some finite constant, but it doesn't vanish anymore.
I see. I see.
Yeah, thanks for reminding me to say this. This is an important point. So yeah, you can anticipate the breakdown of this formula just by looking at the details of the temperature dependence.
I see. Thanks a lot. Yeah.
Blaise, is it correct to say that for z less than d plus 2, the system is somewhat unstable? Will you?
Z less than d plus 2? Why would you say this?
Because as you said that your rho n is going to diverge when your t goes to 0 limit.
Sorry, let me be more precise. So here, z is less than d plus 2 whenever this formula is correct. So in this case, everything is fine. This formula is just saying that the normal density vanishes at 0 temperature. And so the 0 temperature effective theory that describes this ground state is just it's exactly the same as these superfluid gas of free phonons.
Yeah, I got confused because your CIR square has a temperature dependence too. That's what you are saying.
Yeah, yeah.
So this is.
Yeah, this has, for the Lifshitz case, this has, we're calling this CIR because it's kind of natural to call it CIR, but I agree that it's not the same as an actual IR light velocity as you would have for z equal 1. For z equal 1, this CIR would not be temperature dependent. It would just be some number less than 1.
Okay, thanks.
But what we're saying is that even for z greater than 1, we find that, so this formula is correct even for z greater than 1, provided that z is less than d plus 2. And then this quantity has some temperature dependence. And from the detailed temperature dependence, you can predict, you can see that something goes wrong when z crosses d plus 2, because then rho n would diverge as t goes to 0. But then our result, what we computed using this holographic system, is that for z greater than d plus 2, when you do the calculation carefully, you find that the normal density goes to a constant, a non-vanishing constant, rather than blow up. And that is completely different from this universality class, which is described by the free gas of superfluid phonons at 0 temperature.
Yeah, great.
So just to convince you that, we did go through the calculation and that things are as we say they are. So these are the numerics that we ran for, so we worked in d equals 2 mostly. And we have set, here I'm showing you 3 cases. One has z equal 1. So this has z less than d plus 2. The dots, the empty circles are numerics, and the solid black line is this formula with this precise coefficients. So which is the same as this formula, of course. And you can see that the two match very well. Now, this case is for z equals 2, which is still less than d plus 2, which would be 4 in our case. And then again, you see that this formula, which is the black solid line, matches the dots very well as you go towards low temperatures. And then we have a case where z is equal to 12, which is greater than d plus 2. And there you see that, so we show rho n minus rho n 0, so we've subtracted off this constant. And this was to exemplify that we can also compute analytically the leading temperature dependence, which in this particular case goes like t to the 2/3. And so you can see that things match very well as well. So the summary so far is that the normal density vanishes in holographic phases where the U1 symmetry breaking deformation dominates over the particle hole symmetry breaking deformations at low temperatures. And as I've tried to explain, the calculation we've done reproduces the expected EFT result for phases that have an emergent Lorentz symmetry. So by this I mean z equal 1 in the IR. And it extends it to Lifshitz-invariant phases with z less than d plus 2. We show that the same formula is still true when z is greater than 1. However, the formula breaks down for z greater than d plus 2. And in this case, we show that instead of this diverging, the normal density is actually non-vanishing. And as I've also stressed, this is completely unrelated to whether you have a charged extremal horizon or whether all the charge sits in the scalar condensate outside the horizon. And if I now go back to these results by Herzog and Yaron, it explains these features that they had found. We can show that for the values of parameters that lead to these curves, then here you would always get Lifshitz phases with z greater than d plus 2, which is why this thing is asymptotic to something less than 1. And all of these have either ADS or Lifshitz with z less than d plus 2. So that's also a nice cross-check. Let me give you some open questions. So just to remind you, this is the result that we found for Lifshitz-invariant phases with z less than d plus 2. And as I mentioned in the previous slide, this CIR has some temperature dependence. And now if you plug in this formula in the formula for superfluid second sound, then you would find that it vanishes as t goes as t2 minus 2 over z. So second sound vanishes at 0 temperature. Now you may remember that in the Landau case, we were having this. So a non-vanishing superfluid second sound mode. So, you know, although it seems that the formula is the same as the one that you would establish using the description in terms of a gas of free phonons at 0 temperature, somehow the consequences for these Lifshitz phases are pretty different. And so I think it's an interesting question to work out what would be the equivalent of this quantum effective action for Lifshitz phases that would explain this vanishing of the superfluid second sound mode. Because, you know, naturally you would expect that if at 0 temperature your system is made up of free superfluid phonons, then second sound should not vanish. Yet somehow it does. So there's something to understand there. I think there's going to be interesting things to understand by considering how you generalize this relativistic quantum effective action to z greater than 1. Still, for z less than d plus 2, there must be qualitative similarities to the free phonon gas picture because the formula for rho n is the same. However, for z greater than d plus 2, there are going to be differences. In particular, I think it must be that somehow this is some kind of interacting ground state. This free phonon gas picture breaks down. So the last part of my talk is about this. The question is, how much time do I have left? Probably not much.
Yeah, you have to conclude in 2 minutes, 2 or 3 minutes.
Okay, so let's go back to 2 minutes should be enough. Let's see now if we can explain qualitatively, or at least understand qualitative aspects of these results. So to capture this, the type of behavior that is shown in this plot, we want to consider a more general action, a more general gravity action. So now I'm introducing some neutral scalar, real scalar, that is not going to condense. And we want to consider more general ground states that have this extra hyperscaling violation factor. It doesn't matter much. Just to say that we add some bells and whistles to our holographic action. And the main thing that this allows us to do is to have the following RG flow. In the UV, we have ADS 4. So we work in a 4-dimensional bulk. And there's a UV coupling G, which is for people who are familiar with ADS-CFT, which is related to the source of this scalar operator. And we can use this coupling to deform the CFT. So there's a critical value of the coupling where we will get another copy of ADS4 in the infrared. But then when we cross this point by varying this coupling G, then we'll go from a phase that has 0 horizon electric flux at 0 temperature to a phase that has still a charged horizon at 0 temperature. And in these geometries, the condensate always acts as an irrelevant deformation. So that means that qualitatively, these geometries are the same as in the normal phase. And then when we add the condensate just acts as a small deformation all the way to 0 temperature. And now when we go through the same computation. We compute the normal densities and superfluid densities in the same way that I've described. And we can easily find results that look like this, where as we vary, so this is our G, which is the source of the scalar over chemical potential. So for sufficiently negative G, we find that the normal density, so I should say this is rho n over rho total, and this is rho s over rho total. So it's easy to cook up a model where you see the same qualitative picture arising as in the results by Blaise. I think, this is not to be taken extremely seriously. I'm not saying that we have a holographic dual of anything. I'm just saying that by playing with what I was telling you before, by playing with the spectrum of irrelevant deformation around the ground state of these holographic superfluids, it's pretty easy to come up with solutions that mimic these experimental results. And the lesson I would draw from this is that this suggests that in real systems, whether the normal density vanishes or not, depends on the spectrum of deformations around the ground states and the nature of the interactions in the EFT that controls the dynamics around this ground state. And in particular, as I was stressing before, the results by Blaise tell us that somehow BCS is not the right framework. And it could be that it's not the right framework because it doesn't have the right kind of interactions, that the condensate deformation is too strong in BCS theory. And maybe there's a way of modifying BCS theory so that you modify the spectrum of interactions. And that's it. Thank you.
Thanks for this very beautiful talk, Blaise. Yeah, we can have some questions now from the audience.
Hi, I have a question.
Hi.
So when we talk about the phase diagram of high temperature superconductors, we have
Yes.
On the x-axis we have the doping parameter, right?
Yeah.
Now, so first thing is that is there what would be the analog of this doping parameter in the holographic superconductivity picture?
Oh, yeah. So.
And the second,
good.
Okay, I'll let you answer that.
So I'm not doing, you shouldn't take this seriously in the sense that this, let's see. So doping, as I said at some point, has to do with the chemical composition of the material that people are considering. They're substituting some atoms for others, etc. So it adds charge carriers. Here in my holographic system, what I'm doing is I'm varying the, go back. I don't really have a picture for this, unfortunately. So this scalar field has a source in the UV, and I'm varying it. And the thing is that varying this source has the same qualitative impact on the system as varying doping would. So in particular, something we've checked is that as you increase this parameter, then you also, as you go in this direction, you see that the charge density increases.
The scalar field is a measure of the charge carrier density, basically, right?
The scalar field is a measure of what?
The density of charge carriers.
Not quite.
No.
It's more complicated than this, but what we've checked is that increasing the value of the scalar source, it also increases the charge density. So somehow this is going in the same direction as increasing doping would in cuprates. In the same way, when we break translations a little bit, so you expect that doping increases disorder in cuprates because you're adding, more atoms of a different kind. So you're making your crystal less symmetric somehow. And in our case, we observe the same thing. If we break translations weakly, then we see that increasing this source is also increasing the strength of the translation symmetry breaking. So this parameter is not doping per se, but it seems to be, it's not doping, but it has an effect on the system which is qualitatively similar. And in particular, I think what I want to stress with this picture is not so much that you should take this seriously as a model of cuprates. You should simply take this seriously as what varying some external coupling, how varying an external coupling can affect the quantum critical properties of the underlying ground state. And this is really what we're trying to do here.
Okay. So, I mean, just wanted to ask a second question. So, when you say that, this is not to be taken as a serious model of cuprates, my question was actually going to be that I haven't kept up with recent developments. Has anybody recently, tried to relate the other parts of the high temperature phase diagram and to give them a holographic interpretation?
So you see, here we run into the problem of what it is that you want to achieve using holography. And I think maybe, let's say 10 years ago, people were very keen in trying to get the holographic dual of, let's say, high Tc superconductivity. But that, I think this is a bit unrealistic, because these dualities, the way they work is you identify the two systems at a microscopic level. But this is never going to happen. I mean, I think it is very unlikely that this will happen as far as cuprates and gravity are concerned, because, I mean, cuprates are characterized at a microscopic level by some crystal, some underlying crystal, and I just don't see a way of encoding this in my holographic gravity dual. I don't know how to encode the same crystalline structure. However, what I can do is I can try to see what happens in the IR, where all of these UV details are washed out. And you might expect that, systems fall into the same universality class. So here, for instance, in this particular exercise, what I'm trying to do is, I'm not trying to get the holographic dual of these particular cuprates. I'm asking, let me take a strongly coupled superfluid where I can calculate things and ask the question, is there something that I can do in order to change the dynamics at zero temperature in order to get a non-vanishing normal density, which at least these experiments suggest is happening also in cuprates. What needs to happen in order for this to be true? And what we see in this holographic system is that this happens depending on the spectrum of interactions around the ground state. And my hope is that then we can find a way of translating this in some more concrete condensed matter model. Take the Hubbard model and then play with interactions.
Right.
That can have a similar effect, that this gives you some inspiration, some guiding principle by which you might get a non-vanishing normal density that has nothing to do with the presence of disorder and pair breaking effects and all of that. If that's
there is this formulation due to Xiaocheng Zhang, the SO5 theory, right? I don't know if
which
you're
theory,
familiar.
sorry?
It's based on the gauge group SO5.
Okay.
And so Zhang and Demmler, Eugene Demmler, so they did this work back in 2000, starting in 95 till 2005. And basically what they show is that if you look at the Hubbard model, it has a certain set of emergent symmetry, effective emergent symmetries. And those symmetries correspond to the generators of the SO5 algebra.
Mm-hmm.
And then they construct a set of order parameters. One of those order parameters is the superconducting charge density, or the superconducting order parameter, and the other three are the Neal order parameter for the antiferromagnetic phase.
Mm-hmm.
Right, and so they combine these 5 order parameters into a single 5-dimensional vector, right? And then they say that depending on the direction this vector points in, you have either an antiferromagnetic phase or a superconducting phase or something in between. So
Mm-hmm.
I don't know. I suppose that is not in fashion anymore.
I don't know, to be honest.
Okay.
I didn't know about this theory. I'd be happy to learn about it.
Okay. All right. Thanks a lot.
Okay, so we have time for like 1 or 2 more quick questions.
So, Jyotirmoy, maybe if I can go back to your question.
Yeah.
Which I didn't really, I mean, as you could see from the talk, I'm not really answering it.
Right.
In the sense that I cannot tell you what is the correct zero temperature theory that would describe these systems.
Right.
Because we always work at some small non-zero temperature where we can define some hydrodynamic expansion.
Right. Right.
But I agree that the question you were asking would be the natural follow-up, and it would be very nice to be able to do that.
Yeah, I guess the hydrodynamic description would sort of break down. You know, this normal hydrodynamic description would not be valid if you strictly wanted to take the temperature going to 0. I mean, there's a very good work by Sandeep and company where they actually try to keep this parameter somewhere in between. The omega lies somewhere, in chemical potential. And what they find is quite curiously, I think they have dispersion relationships which are log omegas. So it's basically a non-local theory. Okay. And something which they don't say in their paper, and I believe is, this non-locality is somehow a manifestation of extra degrees of freedom, which they are not keeping track of.
But we know, yeah. Okay, I would say that we know what these, at least I have some good guess for what these extra degrees of freedoms are supposed to be. Because in the holographic system that they're describing, we know that on top of modes that you could think of as, let's say, conventional, these hydro modes, there's also this whole tower of IR modes, the one that would coalesce into branch at zero temperatures exactly.
Yeah.
But at non-zero temperatures, if you're at temperatures much less than chemical potential, then these modes are not far away, they're close by. And so I think that somehow what they're seeing has to be related to this tower of IR modes that are around. And the calculation does not capture that. And they don't claim that it does, but I think the fact these logs that they find are a signal that they're approaching nearby modes. And I would think that these are the modes that they're approaching.
That's right. That's right. That's very right. And I'm not very sure what happens to the superfluid case, actually. That's why I was looking for some.
Yeah. So the superfluid case I would expect is kind of similar. But here let me stress that, as you were saying, these guys, they work in the limit where T is much less than omega in Q, much less than mu.
Right.
But we work in a different limit where omega and Q are much less than T, much less than mu. So all of these dangerous modes, they're pretty far away. Because temperature is finite, we don't take it to 0. We take, we consider excitations that are on length scales and time scales that are much longer than the scale set by temperature. So these modes that we think might be giving rise to these non-localities, that there will be at scales of order temperature, 4 pi t, 6 pi t, etc.
Yeah.
So I think we, in the calculation we do, we're safe on that. But I agree that at some point it's desirable to take the opposite order of limits. All I can add to this is that.
So somehow it feels that the superfluid theory has the Goldstone boson. So
Yeah.
I mean, I mean, so do you have any impression of if you just look at the hydrodynamic theory, okay, does the naive limit work? Like, if you want to write down a consistent theory at 0 temperature, just taking a naive limit on the hydrodynamic theory, so does that work out? Like, because this is somewhat, I'm saying that
so
keep the transport coefficients or your densities, as parameters. But if you're just looking at the theory of the fluctuations, like, the velocity.
Yes. So this we haven't checked because, for instance, I think if I understand your question correctly, you're asking, let's say that we now take the 0 temperature limit and we compute the spectrum of quasi-normal modes.
Well,
what the hydro modes are doing
would not be much different from what you see from the black hole. That would be very similar to what you see from the black hole. So quasi-normal mode behavior would be, I think, quite predictable. But what I was wondering is, how does the truncation work? I mean, because the temperature, if you try to, maybe it's not a very good question. If you try to freeze the temperature at somewhat, very close to 0, then you are in some sense losing a degree of freedom. So I'm not very sure if it is possible to independently write down an equation for the phi, which would, so something like, Sohn had done, for instance. Okay.
Yeah.
So I guess what I'm asking is, can you do something like that for your Lifshitz case? And, can you find?
Yeah, that's one of the things that I was saying I would like to do.
Okay. All right.
It might be possible to do it, but I don't know what will happen. I think ultimately, so at some point I was, let's see, I was making this point right here about the Lifshitz system. But so this is saying that, your omega goes like t to the 1 minus 1 over z times q at low t. But I would expect that if you take the 0 temperature limit first, somehow there should be some interpolation to this. Omega goes like q to the z. This is what I would expect the 0 temperature dispersion relation should look like.
Interesting.
And it might be that you can see this by, tracking this mode starting from non-zero temperatures and then going to low temperatures and see that the dispersion relation changes from this to that. But this we haven't done.
Right.
Because, for instance, I would expect this to be the correct starting point for the quantum effective action. We should write some quantum effective action that's compatible with this.
I just want to make a comment on this Jyotirmay's observation, and is that I think what Shiraz and all these people find is relevant for the shear viscosity and the shear mode. But if you are just interested in understanding the thermodynamic properties, we should follow from a quantum effective action like approach. I don't think these things are so relevant about the other. One should be able to understand it pretty clearly, I think.
Yeah, but you'd want to also at some point look at fluctuations.
Yeah, fluctuations for sure. Yeah, fluctuations. Fluctuations are typically are going to change your. It always changes hydrodynamics into something non-local. That happens even at finite t. You find this omega to the power 3/2 tails. So, but I think it's still the question is about just to understand the topic, whether how does this rho n should behave. I think you can use the quantum effective action without any problem.
Yeah.
Sorry, what was the reference about Shiraz you were talking about?
I think they were talking about the shear viscosity. I think that is the shear mode. That's where the problem lies, right?
No, I think
there's a log-like divergence that you cannot cure even if you even if you, I think, tune eta to be.
I was referring to Sandeep's latest paper, where she asked.
Okay, I don't know that. Okay.
Yeah.
Sorry.
I think very recently Sandeep has written a paper on, where it, and try to find out the fluctuations by keeping the temperature scale lower than the omega scale. So I was referring to that one, that kind of analysis would be, I think, more relevant. Yeah,
but but I will be surprised if it has to any bearing on understanding thermodynamic properties or like this.
No, but you're right. What they observe is these kind of effects actually, these log omegas actually come in at second order.
Yeah, so, that's what I was trying to say. It's a more higher order effect.
Yeah. If you're thinking about, the equilibrium, I guess the equilibrium is pretty much, we know how to describe the equilibrium, that if that's what you're saying. Yeah, I mean, equilibrium is very, but I think the whole question about what these modes and hydrodynamics is the near equilibrium behavior. And
no, I think it is certainly a very big question of how to understand fluctuations. And indeed, I think the next talk will be on that also, Alex Soloviev. Yeah, so I think it is, this whole theory of hydrodynamic fluctuations is a very new topic and very exciting topic too, yeah.
So yeah, I just posted the paper that I hope we were discussing, because that's the paper I was discussing with Jyotirmoy.
Right.
Okay, so I think to conclude.
Just before breaking, I hope, Blaise, you're doing well. We haven't spoken.
Yeah, yeah. It's been some time.
Yeah, all right.
It's nice to catch up.
Yeah, it was wonderful to have you here, and we will also look forward to your longer paper with very beautiful work. And it's thanks for sharing with us. And
thanks for having me.
Okay, so we thank you again, and applause for your talk.
Thank you all for listening and for all the interesting questions.
Thank you. So goodbye.
Goodbye.
Bye.
Have a nice evening, all of you.